Hi, welcome to another lecture on Calculus 2. Today we are going to continue our conversation about trigonometric integration. Last time we looked at products of sine and cosine, and for today we are going to look at product of powers of tangent and secant. So we did several examples of the first case in the previous lecture, and today we have this particular integration in mind. And in fact, this type of integrals are closely related to the two examples I talked about last time. Of course, from mathematical point of view, we do the most general case, and in specific instances that you see in engineering, the powers are going to be certain particular numbers. Now, let's go ahead and see what is in store for us here. I've written here some of the main identities from either trigonometry or calculus 1 that is going to be handy here. First set is just Pythagorean identity. So you're familiar with this from trigonometry. The next four are differentiation formulas from calculus 1. So we know derivative of tangent is secant squared, derivative of secant is tangent secant. And then if you apply this thing with the power rule, derivative of tangent to power of n is n tangent to power of n minus 1 secant squared, and derivative of secant to power of n is n tangent secant to power of n. So we need these to proceed. Now best thing to do is just to write some example cases. Just like in the case of sine and cosine, it depends a lot on what type of powers we have, and that's going to dictate to us what approach to take. So first case we are going to look at is when the power of secant is an even number. So suppose power of secant is an even number. What is that going to do for us? Let's take example. Suppose I have, say, secant to power of 6 of x, and then tangent to power of, say, 8 of x dx. It doesn't matter what we have here on the tangent. What we notice is that when you take your variable to be tangent, then the derivative of tangent is going to be secant squared. So what we are going to do is to separate a secant square and then convert the rest of the secant to tangent by using this trig identity. So for this to work, and for us not to get stuck inside the radical or such, it is necessary for this power to be even. Let's see how does this thing work. So we said we are going to separate a secant square, and that is going to play the role of our tangent. By now we are left with secant to power of 4 of x, tangent to power of 8 of x. Now we say the secant to power of 4, due to the fact that the exponent is still even, we can write it as square of secant. Secant square of x squared will make that. The rest we just carry through. Now what? Well, secant square can be converted to tangent. So 1 plus tan square of x to whatever power applies, then tan to whatever exponent we have here, and then this is derivative of tangent. That is the magic that makes it work. So if I make a substitution that u is tangent of x, then du will be secant square of x dx, and as a result this is going to be 1 plus u squared squared, then u8, and then du. Well, this became a polynomial integration, and that means essentially the problem is over, because it's very easy from here on. To u squared plus u4, I just have to do a bit of algebra, and then I'll be all set, because now I have u8 to u10 u12 du, and u9 over 9 to u11 over 11 u13 over 13 constant. We do our back substitution, so we'll have our answer. So that wasn't bad at all, because everything was just right. The numbers worked with each other very nicely. Yeah, so the secret was here that the secant power was even. When I split the power 2 off of it, the rest of it is still even. I can write it as a power of 1 plus tan squared. If this wasn't even, that wouldn't be even. Here I will have a fractional number, and then fractional number would mean that I have a radical here, and I'm back into another difficult problem to handle. So this is in fact an easy case. Okay, now what if the power of secant wasn't even? What other choices we have? Another situation that saves the day is if the power of tangent is odd. If the power of tangent is odd, then we are going to make use of this formula. Let's see how does that work. So let's take an example. If I know that the power of tangent is an odd number, let's take a case. Suppose I have secant to power of 5 tangent to power of 5 of x dx. Now it doesn't matter what we have for the secant, odd or even. Well, if we had an even, we would have the previous approach as well. If that's even, this is odd, then like your day, you have two ways to follow, and then you pick the road that is less algebra. However, here secant power is odd, so the previous approach doesn't work, but now we have this one. So how do we approach in this case? In this case, I'm going to set aside a single tangent and single secant as a derivative of secant, and then convert everybody else to secant. So that's the trick. So I'm going to write secant tangent dx, and that's going to be the derivative of a secant for us. And then I will have, now I have secant to power of 4 of x, tangent to power of 4 of x, and the rest of stuff. I take u to be secant of x. So du, that's the formula we said we need for derivative of secant. We need, this is secant of x, tangent of x dx. So that's going to be my du. How about here? Well, I need everybody to be in terms of secant, and that's why I need to convert my tangent to secant. So how do I do that? Secant, I leave it alone. Tangent, I write it tangent squared. So if this was 6, this will be cube, of course. Secant of x tan x dx. One more step to convert everybody to secant. So I'll say secant to power of 4 of x, tan squared. Tan squared is secant squared minus 1. So that is the secret that makes it work. That's a secret sauce. Secant squared of x minus 1 is tan squared. Now you're squaring it, and then the leftover, secant of x tan x dx. So what happens now? Let's go to the u language. So that's going to be u to power of 4 That's going to be u squared minus 1 squared, and that's going to be du. So again, we are looking at a polynomial integration. That means essentially the problem is 99% over, and we have an easy time now. U squared u4 minus 2u squared plus 1, so u8 minus 2u6 plus u4 du, I believe. And then let's go ahead and do substitution and integration at the same time. So it's going to be secant to power of 9 of x over 9 minus 2 secant to power of, what's that, 7 of x over 7 plus secant to power of what, 5 of x over 5, and throw in a constant for good measure. So that handles that situation. Okay, now what if neither of these cases were valid? Neither the power of secant was even, and nor was it that the power of tangent is odd. Let's go ahead, take a case, say we have a simple case, say secant to power of 7 of x dx. So our first approach doesn't work because secant was supposed to be even here. Second approach doesn't work because tangent was supposed to be odd there. Now I have just a secant, and then we don't even have a tangent for it to be so if you wish to think about having a tangent here, the tangent power is 0, so our previous approach doesn't work either. This type of problem is going to be approached by something that we did similarly in the previous lecture. We had tangent cube. This is in the same family of problems. We are going to approach it by essentially integration by parts. And so it's not just trig substitution, rather the approach that we had at the very beginning of the semester, that's going to be crucial. Together with that, we are going to essentially introduce an approach for these type of problems that's called a reduction problem, a reduction method. Reduction means we are going to lower the exponent. So secant 7 can go to 5, 5 can go to 3. Well, we have done the 3, but essentially you can keep going. 3 goes to 1, and then integral of secant, you know itself from calculus 1, logarithm of secant plus tangent. That's how we do it. So we are essentially introducing a new idea here, and that's the idea of reduction. So reduction means reducing the power. Typically the power reduction happens while the problem stays in the type of a statement it is in already. So first what we do is we see that well, I don't have an tangent to play with. I can have a secant square separated. That's going to be derivative of a tangent. Let's see how it works for me. So I'm going to write this thing as secant to power of 5 of x, then secant square of x dx. So I'm going to separate that. Then I can write this thing as secant to power of 5 of x, and instead of secant squared was 1 plus tan squared, so I write it as 1 plus tan square of x dx. Now what? Well, when you multiply this thing, one of them is just secant to power of 5 of x dx, and then the other one is secant to power of 5 of x tan square of x dx. Now we see the emergence of reduction. This is 7, this is 5, but of course we have a long ways still to go. Next up, well, I seem to have jumped from frying pan into the fire. Like now I have two of these functions, the total power is still 7. How do I proceed from here? I leave this thing alone as an indication that I'm really doing reduction. Now secant tangent, we take u just like what we did for the secant cube. We take u to be let's see, what should I write it? I take it to be tangent of x. So let me write it here maybe. So let's separate that problem. Secant to power of 5 of x, tan square of x dx. And this is where integration by parts kick in. So let me remind you, we have u dv was equal to uv minus integral of v du. So that's the approach we are going to take. So let me clean this up and write this thing here, and maybe separate this thing so that it looks clean and nice. So we said that we are going to take u to be tangent of x. So du is going to be, of course, secant square of x dx. Well, dv is supposed to be whatever is left, which in this case is secant to power of 5 of x dx. Now the question is, what is v? So v is well, let me make a correction here. I didn't write this thing completely. We have left u is tangent of x, and dv, the leftover, is secant to power of 5 tangent dx. So I was missing tangent of x dx. Now what is v? What comes to rescue is a formula I noted here. If you have secant to a power, you differentiate it. A tangent is born and secant stays to the same power it was. Okay, secant to power n, you differentiate, is n, tangent secant to power of n again. So over there I have tangent times secant to power of 5. The antiderivative of it will be secant to power of 5, except that it's missing this. I have to put this thing back. So over there, if you want to write this problem in a integral notation, it will be tangent secant to power of n. Antiderivative of this thing is secant to power of n over n. Now I have dropped all the x's and dx's and everything. If you want to insist, if there's an x here and there's an x here and there's an x here and a constant here. So what we have here is antiderivative of this thing. We needed that introduction to see quickly. The antiderivative is secant to power of 5 over 5, and we dispense with that constants. So u times v will be the product of these two. So I'm going to have tangent secant to power of 5 over 5, and then minus v du, this times that, is going to be what? V times du, secant to power of 5, secant to power of 2, it compresses to secant to power of 7. In the denominator is a 5 x dx. Let me write this thing better so that I am not violating my own rule of keeping your... So tangent of x, don't have enough space here, this was secant to power of 5 of x over 5. Okay, what have we achieved? We have achieved this. It looks like we went back where we were. Let's write this thing down and see what have. we have tangent of x secant to power of x over 5, and then I have integral of secant to power of x secant to power of 7 of x over 5 dx. So I have secant to power of 7. Then I split it into two pieces. Out of that is born smaller case of the problem I had to begin with, and another piece which is same as the integral that I wanted, except with a different coefficient somewhere in it. So this is in fact an application of that self-referral type of problems, meaning we start with an integral, we end up with the same integral with the different coefficient. We take this thing back to that side, unite them with its own type, and then we are essentially done. Better than 90% of the problem is done. I take this thing to the left hand side, so now I have I take the 1/5 out, then there is a secant to power of 7 of x dx. The original was just a plain secant to power of 7. On the other side, I am left with these. I have a secant to power of 5 of x dx, and one term is borne out, which is tangent to power of x secant to power of 5 over 5. Now let me see, can somebody take this thing to almost a conclusion? What do we do next to figure out integral of secant to power of 7? What do I do in the next step? So try to finish the problem. Okay, it's very important you finish this problem. Of course, when you have these two integrals, 1/5 of something plus 1 of that thing, well, of course that is 6/5 of that integral, secant to power of 7. Right hand side, I have the same thing I had before, secant to power of 5. From 7 to 5, that's a reduction, and then I have this tangent of x secant to power of 5 of x over 5. What do I need to do next? I multiply by 5, 6 to make my formula clean on one side. Secant to power of 7 of x dx, multiply by 5, 6. This becomes 5, 6. Integral of secant to power of 5 of x dx. 5, 6 times that makes it 1, 6. So it becomes tangent. So the 5 cancels that 5. Tangent of x secant 5 of x now over 6. And of course this integral is going to have one constant in it when you perform it, so we might wait until the very end to put that constant. Okay, so what happened again? So I wanted the integral of secant 7. I have the answer in terms of secant to power of 5. Now can you guess what do we do next? Why do we solve the problem this way? This is not completed, of course. Now I'm stuck with another one, but can you think of what is going to happen here? That is, if I were to ask what is secant to power of 5 of x dx, can you guess what would be on the right hand side? Well, typically is a very simple pattern here that you can guess, or to be sure you can always start with secant to power of n. So you can start with an n here and see what happens. I strongly recommend you do that. And the connections are very simple. If this is 7, we see this is the 6 and that's the 5. So that essentially means if this is n, this is n minus 1, this is n minus 2, this is n minus 2, this is n minus 1, this is n minus 2, and so on. So maybe we go ahead and write the general case. So if I had n here, this is going to be n minus 2 over n minus 1, and this is also going to be, well, n minus 1, and then I have the power n minus 2 here and n minus 2 here and so on. So let me write the rest of it. So I try to color coordinate it so that you see what's happening. This is tangent of x, secant of x to power of n minus 2. So let me write this thing a little bit better. So this becomes our reduction formula. There are many reduction formulas of this type in calculus. And then, well, with that idea, then you can apply secant to power of 5. That's going to be reduced to secant cubed. Now we can say secant cube, we have already done it, but if you wish, you can apply it again to secant cube, find that one, and at the very end it comes down to secant to power 1 of x, and that integral, you know, we have seen this thing several times. Secant of x by itself at the very end, that one needs to be done in a completely different style. Secant of x plus tan x, and then at that stage you're all done. So I'm going to ask you to complete this process so this video doesn't become too long, and the rest of it is going to be the algebra that you should be able to carry through. Okay, so that was a story of one of these problems. You can look at this from different perspectives again. So maybe we do, let's go back and see what we did. So if secant power is even, and this is the approach to take. If the power of tangent is odd, this is approach to take. If neither of those applies, so the power of secant is odd, then we are facing a reduction, integration by parts, self-referral, all of those things come in, and that's very similar to the problems we had done with respect to referral problems before. Let's do one last one of these things. So what if I had tangent? Well, if tangent power is odd, I'm set, but if the tangent power even, what do I do? Let's go ahead, do an example of that as well. So power of tangent is even. Essentially, we had an example of it here, but let's make it separate example. So suppose we have tangent to power of 6 of x dx. How do we proceed? So again, we remember to split this thing and then convert it to then use the substitution that we have. So what we do is that this power is even. That suggests that I separate tangent square off of this. Tangent to power of 4 can be converted to secant, and that can be attacked individually. So I can write tangent. Tangent, you remember way back here. Tangent is secant squared minus 1. So I can write this thing as secant square of x minus 1 squared, tangent square of x dx. And then I just multiply through, so I'll have this secant to power of 4 minus 2 secant square plus 1 tan square Now we are gonna take this thing individual integrals. Secant square, excuse me, secant to power of 4 of x, tan square of x dx minus 2 secant square of x tan square of x dx, and then I have tan square of x. The substitution that comes in handy here, you remember derivative of tan was secant square. That is what saves the day. Derivative of tangent is secant square. So what we write here is secant square of x, secant square of x. Let me write it like this. And tangent squared by itself, when tangent squared by itself shows up, tangent squared by itself is just secant squared minus 1. Now let's see if this substitution is gonna show the light. If you take u to be tangent of x, then du is secant square of x dx. So this is u squared, this is du, and secant square is 1 plus tan squared. This is 2, this is u squared, and this is du. And secant squared dx is just derivative of tangent, so this thing is already tangent, or let me write it just u. I have this minus 1, it's kind of an odd man out. Antiderivative of 1 is just x. So now I just perform the integration, so I have u squared plus u to power of 4, and then minus 2u squared du. And this one is already done, is a u minus x. I take my derivative to u squared, and 2u squared becomes minus u squared. Antiderivatives become u to power of 5 over 5 minus u3 over 3 plus u minus x. Out comes tan to power of 5 over 5 minus tan 3 over 3, and u was tangent of x, and there is this other x out, and at some point we had to add a constant, so over here we put our constants. So rather twisted, but it can be done, and perhaps you want to find out a way of doing this thing by reduction. Okay, we did several examples of this problem. They gradually become more and more complicated. As the powers go up, the amount of algebra can increase, and we might settle for a reduction formula in those cases, or try to develop formulas in general. So what we learned essentially was, we practiced many trig formulas, the derivatives of the trig formulas, and as I mentioned, to see a real example, you have to sit through lectures on calculations of either gravitational field or magnetic field and such. They both of them show such characteristics. Okay, until next time, good luck and God bless.